Good afternoon, guys. My name is David Eastwood, Geotech Engineering and Testing. Thanks for sharing your afternoon with me. We're going to be talking about geoforensic evaluation of City of Sugar Land Police Station, Highway 6, Sugar Land, Texas. If you all look at that, go out to Sugar Land all the way from Houston, it's out right there on Highway 6, nice building. Pictures of the project, that's what it looks like if you look at it. Nice building there, nice architecture. Notice the trees out here next to the foundation. This is the kind of a southeast side of the building. You can see the locations. They got trees here and trees right next to the foundation. Look at the drainage, negative. Southeast side, trees. This is the northwest side. Again, big oak trees. So it's a beautiful two-story steel structure with poor drainage. A lot of trees. Look at in here, the trench in here, they filled it up with gravel next to the foundation and put a sprinkler system in it. Some more pictures of the site. So about a year ago, we were contacted by City of Sugar Land. We were asked to look at their building, and the building had distress on it. They had cracks and stuff. The doors were sticking. Sheetrock was cracking up. The studs were bulging. Tiles were cracking. So we went out there and looked at the project, developed a project timeline. We did site visits, did field exploration, we did laboratory testing, engineering analysis, developed the reasons for distress, and we told them about the repairs. A couple of things I missed at the beginning is, of course, my name is David Eastwood with Geotech Engineering and Testing. The firm has been around for about 38 years. We do geotechnical, environmental materials, and geoforensic work, failure evaluation of the buildings, pavements, slopes, bridges, and we work all over Texas. We have our own rigs, so that's kind of a commercial there. Project timeline. The building was structural drawings was developed in or about 1994. And they put this building, the two-story building, on top of expansive soils on spread footings. And these spread footings were 3 foot to 6 foot below the final grade. And they were like 5-6 foot square spread footings. In 1996, they added 2 wings to it. Well, in 1996, the building was built. In 2004, they added 2 wings to it, one on each side. And we were contacted in December of 22 to go out there and look at it and figure out what's causing all the problems they have. So we went out there to look at it. These are observation points. If you look at it, these are all the points that we went out there that there were signs of distress, drainage, and all that stuff. So these are called observation points. That's the building, and went out there, started looking at it, and we saw areas of negative drainage that slopes towards the building, the drainage. Presence of a sprinkler system next to the foundation. We saw the gutters draining directly next to the foundation. There's a depression right underneath it. Here's a sprinkler system. See, the planter area is really flat. Poor drainage right next to the foundation. Remember, the soils over here are highly expansive. Again, flat drainage areas. We saw cracks in the brick at the entry area. Again, more gutters draining into the foundation. Lots of trees, these roots going towards the foundation system. These are the roots. Oak trees out there, flat drainage. And the grass was really at the brick line. Typically, we like the exterior grade beams extend 6 inches above the topsoil. So there was no topsoil here, brick line and the topsoil were at the same level. So they didn't, the landscaping was not very good. There was, water could get it, under the foundation system. See the negative drainage here? Water going towards the foundation. Again, trees, flat drainage. Here's a area right next to the foundation. It's filled up with gravel. And I don't think that's a good idea because, having the gravel next to the foundation holds the water and causes foundation movement. So we don't recommend that. You can see again, flat drainage here. Flat drainage in the back. Negative drainage here in the back of the building. Flat drainage. Trees next to the foundation system with negative drainage. Some of the joints, the expansion joints, they had deteriorated and created voids in the pavements so that the surface water can get into the joint, cause the expansive soils to heave. And you can see all the joints. And you look at some of the floor slabs cracked up. More cracked up floor slabs. And there were cracks in the tiles. More cracks in the tiles. See the sheetrock cracking, doors not square. More cracks in tiles, nor the doors not being square. The sheetrock was kind of bulging here, separating. You can see the studs in here kind of bending, even up. And the parts of the area, the building, they had CMU blocks. There was a lot of cracks in the CMU blocks. Go in there, you look at them, there were a lot of cracks in the block system. So if you look at the foundation system for the structure, these are the columns here. This is the slab. This is north. And basically it was a spread footing foundation, about 3 foot thick. And it was like a 6 foot by 6 foot. And about 20 inches thick. And so that was a spread footing there. And, the distance was about 6.5 feet from the bottom of the spread footing to the top of the slab. And when you look at the grade beams between the spread footings, they're put in 4-inch void boxes, but we didn't find any void boxes spaced there. The slab was about 5 inches thick. So, and the beam itself, it was about, 2 foot 8 inches. So we went out and did soil borings. We look at the trees. We did GPR, ground penetrating radar. We did micro elevation, and we did test pit excavations, trying to figure out what kind of a foundation we have as built. We couldn't get a hold of the initial geotechnical report. So we went out there and did some borings here. The red stuff is the boring locations where we did borings. And then the blue stuff is test pits. We did borings 25 foot deep in the exterior, 10 foot deep in the interior. We did GPR, 6 locations in the interior borings, and we did 3 test pit locations. The exterior borings, we try to do the borings close to the trees to get root fibers. These are the truck mounted rigs that we have. So these are various boring locations around the building. We did it last February here, remember? And try to get as close to the building. Next to the trees. Start getting those red clay samples of the Sugarland area. You see that? Really nice fat clays. We check them with hand penetrometer to get some kind of a strength level. We put them in foil and put them in plastic bags. So we check for root fibers. Root fibers tell us the active zone depth. The active zone depth usually is 2 feet below the lowest root fiber. So when we look at the soil samples, we look for root fibers to determine the active zone depth. That's really important for foundation design and pavement design. So these are the borings. We also run in the sand standard penetration test. In this test, you drop 140-pound hammer, 30 inches on the soil. You drive it into the ground, 18 inches. 6 inch, 6 inch, 6 inch. You disregard the first 6 inches and get the blow counts for the top 12 inches. That's ASTM 1586, 140 pounds, drop 30 inches. To get the density of the sand, this is the sand sample. This is the split spoon sample. Split spoon sampler. If the blow counts between 0 to 4, you got very loose, and 5 to 10, loose, medium dense, 11 to 30. And we also measure the water levels. This is with a tape measure with a weight at the end of it. We throw it in the hole and you measure the water level. We didn't find any water on this site. No groundwater. We also did GPR next to the borings in the interior before we drill them to see if there was any pipes, cables, anything around. We didn't want to cut anything. This is a police station, so we didn't want to get them out of commission. So we went out there and with the GPR before we do any borings to find the utilities underneath the floor slabs. Ground penetrating radar uses an antenna that transmits electromagnetic energy similar to what cell phones have. The receiver is located within the antenna and receives the reflected signal. When it encounters soils with 2 different material properties, they call it contrasting dielectric values. It looks like a lawnmower. This is the device in here. That's the screen in here. You can scan it to find utilities, find voids, areas of high moisture. That's kind of what the screen looks like. You got to really know what you're looking at. Here's kind of the GPR in the project site, in the bathroom next to the tiles that we're cracking. We're trying to do borings out there. These are the locations. We try to do a boring right there. You can see identifying the location of the boring. There's no utilities with GPR. We're marking the area. That's the boring location. Again, we found over here, we find a pipe over here, some kind of a cable over here, pipe. So we did the borings where there was no underground utility. There were pipes here. A lot of stuff was under the floor slabs. Again, you can see over here, we do the boring right there, trying to avoid any underground utilities and pipes and cables, water lines, sanitary lines. See again, do boring over here. There's a cable or a pipe over here. Here's the boring and here's the pipe location. Again, we did it all over the place, looking for underground stuff. Before, of course, we do the borings, we had to core that concrete. The slab was 5 inches thick for design. So we core that concrete. There was water, we had to evacuate it all out. Here's about 6-inch concrete cores, 5-inch core, 5.5, 5.5, 6 inches, 5-inch cores. This is the holes we had, is about 4 inches in diameter. Interior borings. We had to use a portable rig system that we have that goes inside the buildings, and we can do borings with it. It drills in there. We had to get clean air in there, so we had to bring in air. This thing gasoline operated, so it's got some, smell to it. That's how we drilled it through the floor slabs, got soil samples. We measured the water levels again underneath the floor slab areas. There was no water. After finished drilling and sampling, we grouted the holes with ground mixture of cement and water and bentonite. Trees, as we showed you at the beginning, there are a lot of oak trees around this building. And a lot of them are pretty close. Some of them are great myrtles here. Some of them very close to the building. One of the other things was we made the elevations using leveling, digital leveling system. I call it zip level system. We got elevations of the floor slabs to get the relative elevation. See how out of level the floor slabs were. So we found the high point was right here, plus 0.7, and low point was right there, minus 1.2. So the elevation difference was roughly about 2 inches, 1.9 inches across the slab. These are various elevation points. We also did test pits around the building. We did 3 of them. Try to figure out the exterior beam depth, soil conditions at the beam level, presence of water, to see if there's any void boxes there, grade beam spread footing connections, if perch water table exists, presence of large tree roots. So we start digging next to the foundation and start going deeper and deeper. We found the spread footing right here. So there was a lot of excavation there. We found root systems. See it again, depth of the grade beam right there. We measured the beam depth, the spread footing width, beam depth. We checked the soil with the hand penetrometer to see what kind of soils we have at the grade beam level to get the strength of it. So we started backfilling the whole thing and compacting the hole after we get our data. Well, test pit number 1, northeast side of the building, from 0 to 5 feet was all fat gumbo clay. The exterior slab was 8 inches, which was designed as 8 inches. Spread footing thickness was almost 15 inches. The design was 16 inches. The width was 60 inches. Design was 60 inches. Spread footing depth was 51 inches, and the design was 54 inches. We didn't find any water in the test pit number 1. Test pit number 2, we had fat clays from 0 to 41 inches. There was no water. The exterior slab was 5.5 to 8 inches. Design was 8 inches. Column width was about 20 inches, which was designed as 20 inches. And test pit number 3, that was located southeast side of the building, from 0 to almost 58 inches, 5 feet, was all fat clay. Hand penetrometer 1.0. Slab was 8 inches, that's what the design was at the exterior. Spread footing thickness 14 inches. Design was 15 inches. Spread footing 54 inches. Design was 54 inches at this location. Spread footing depth was 40 inches, was supposed to be in 55 inches. We didn't find any water here. Void boxes. We look for voids underneath the grade beams, and there was no voids under the grade beams. We don't know if the contractor used void boxes underneath the grade beams or not, but there was nothing there. Laboratory testing. I mean, I'm not expecting to see the void boxes. I'm expecting to see maybe some voids, but there was no voids anywhere. The test we did was classification tests like Atterberg limit, moisture content. We ran some unconfined compression tests, hand penetrometer, and total vein for strength. We ran Proctor tests to see what the compaction of the soil is under the floor slabs. We checked the concrete to see if there's a strong enough compressive strength of it. And we then ran some swell tests to see if how much swelling the on-site soils can experience. This is the soil stratigraphy. These are the exterior borings. These are the interior borings. The dark stuff is fat clays. So you have a lot of fat clays, then you got lean clays, you got fat clay, lean clay. Here you got a little bit of fat clay, then all lean clay. Underneath the floor slabs, you got the fill. And believe it or not, the contractor would put in fat clay fill under the floor slabs. So this thing was on spread footing, and pretty much most of the slab was on highly expansive soils. And here's the kind of fat clay in here. So it was just really a bad design and construction here on this project. The slab was supposed to be 5 inches. Below that, we found in some fill areas 0 to 2 feet fat clay. In some areas was lean clay, which was supposed to be select fill. And then fat clay in some areas all the way down to 25 feet, and some lean clays too. The PIs for the fat clay was 33 to 44, 33 to 50. Lean clay was 10 to 30. And the soils were pretty strong. The strength was not a problem. We didn't have a problem with settlement. Our problem was heave. These are the boring logs. This is the exterior boring B1. And you can see fat clay to about 6 feet here. PI of 52, 37. The lean clay PI was 16. No water. Soils are pretty strong. Here's B2. Got fat clay pretty much everywhere, all the way down. You got a little bit of lean clay in here. PIs of 51, 44, 49. Here's boring exterior B3. Pretty much fat clay everywhere. PIs in here of 40, 35, 25. Here's B4. You got fat clay and lean clays. All the way down, you got PI 33, 36, 40. Remember, PIs greater than 20 is considered to be expansive soils. Here we got the boring B5 exterior, fat clay 0 to 1 foot. Below that was lean clay. And the PIs of 30, 24, 30. Still expansive. It's lean clay, but still expansive soil. In the borings here, some 5-foot borings interior. We couldn't go deeper because we hit something. And so we have some PIs of 36, 40 underneath the floor slab in the fill. You have the PI of 36 in the fill. That's not good. Here again, we got fill. We got a PI of 38 in the fill. Below that, you got PI of 39 and 40. No water in the interior. B9 interior going to depth of 10 feet. You got 2 foot of fat clay with PI of 33. Again, I mean, why would the contractor put fat clay underneath the floor slabs? PI 35, 12. That's B. Let's see. This is B10. 2 foot of fat clay. Oh, lean clay. And then below that, you got lean clay, PI of 34. Below that, you got fat clay. Plasticity index of 45. The fill was PI 19, by the way. And below that was a lean clay with a PI of 10 in the interior. Boring 11 interior was only 5 foot because we couldn't go deeper. The fill had a PI of 44. And fat clay, fill, and natural soil had PI of 37. We ran some Proctor tests trying to figure out the compaction of the soil. So we ran a Proctor test. The soil had a liquid limit of 51. PI of 32. We got a dry density of 100 and optimal moisture of 22. We ran another one, again, PI of 52, liquid limit 51, 32 someplace else, 104. So we'll also look at the concrete cores that we cored. Again, we're supposed to have 5-inch cores, and we measured 5-inch cores for most of these things at the boring locations. So concrete thickness was not a problem. We had to cut the cores, cap them, and then put them in a machine and crush them, compression machine. So these are the various cores that we had to put in with boring locations. We crush them, see what kind of strength we have. Design was 4,000 PSI at 28 days. For 5-inch slab, we measured 4,300, 3,962, 4,600, 5,000, 5,000, 5,500. So based on this slab had a proper strength. That doesn't mean the concrete was good, but it had adequate strength. One of the other things we looked at was potential vertical rise. Potential vertical rise, or PVR, is the index property of a soil that indicates basically vertical movement of a soil at a specific location. So we calculate that based on TxDOT 124 method. In this case, we use AASHTO method because the site initially didn't have any trees on it. So we came up with a PVR of about 1.9 inches. So that was the differential. Actually, 1.9 is very close to what we measured out there in the field. The elevation difference on the slab was 1.9 inches. When you look at the borings, we also did some swell tests, trying to figure out how much swell we can get using swell tests. So we used PBR method as well as swell test, and we found out based on the average of the borings, we have 0.39% swell in these soils from the current moisture content, which means almost 0.5 inches. You know, when we run PBR, it assumes the real dry conditions. When we run swell test, we run it from existing moisture. As you will find out, the soils near the surface, the top 10 feet, were relatively wet at this site. So there was not much more swell to occur. Most of the swelling had already occurred. When you look at the interior borings, the PVR were 1.2 inches, 1.4 inches, 1.1 inches, 1.9 inches, 1.6. When you use AASHTO 124E for calculation of the PVR from dry to wet condition. 1.9 is pretty close to what we find out in terms of the differential movement that we measured on the project site. Engineering analysis, we reviewed the aerial photos, we look at the topographic maps, look at the tree surveys, we look at the elevations, we look at the fill on the site and its compaction, we look for water, we look at the moisture profiles. We developed liquidity index profiles, potential vertical rise, rainfall data. We look at the GPR data, and we look at the concrete slab strength for our evaluation. If you look at aerial site conditions, you see the site in 1995, which is basically a prairie with some grass, very flat. They went out there and started building it. This is 2002. The building was constructed. And you can see this is 2006. 2011. 2016. 2022. This is the topo map that shows the area was very flat. Again, we talked about the trees. There's trees all around the building. See all the green stuff is trees. A lot of trees around it. Elevations, we ran some sections on the elevations on the slab. Differential was 1.29 inches. So we ran sections AA, BB, and CCs, get cross-section elevations. Couple of concepts in here. Tilt. Tilt is basically a planar rotation measured over the length of the or width of a foundation. That's y over x. That's the horizontal distance. That's the differential movement across the slab. That's y over x, called tilt. American Society of Civil Engineers, it says you can have a tilt of as much as 1% and a slope of 1%. So a 1% tilt, if you got a slab that's 50 foot wide, you can have up to 6 inches of tilt on it, which is acceptable. Slope is a differential elevation between 2 points divided by a horizontal distance at any locations. So tilt is overall slab, and slope is in between. You can pick a couple of points and get the slope on it. So if you got a building like this and you get elevations on it, and if they're parallel like this, they're experiencing tilt. And then there's basically, we have deformation, which is a change of shape of a foundation system from original construction. Deflection is maximum deviation from a straight line between 2 points. And deflection ratio is deflection divided by a horizontal distance over which the deflection occurs. So if you look at a slab, points 1, 2, and 3, the correct deflection is this right here. The incorrect is between 1, 2, and 3 is this. This is not a correct deflection. Allowable movement, we use L over 360. That's essentially the allowable differential of 1 inch over 30 feet. Overall tilt limit is 1%. Allowable deflection 1 inch in 30 feet. We use Post-Tensioning Institute guideline, PTI, and also Foundation Performance Association guidelines for slab deflection. PTI is Post-Tensioning Institute. FPA is Foundation Performance Association, which is a local organization that I highly recommend the engineers to attend. Lots of good technical programs. FPA. Standards by Texas Residential Construction Commission on distress. Recommended floor slab cracks should not be more than 1/8 of an inch. Your flat work should not crack more than 1/4 of an inch. Separation and expansion joints, maximum 1 inches. Stair cracks, no more than 3/8 of an inch settlement. Carport garage cracks, 3/16. Sheetrock 1/32. Brick masonry 1/8. Joints, gaps in the brick mortar is 1/4 of an inch. We look at the deflection section AA. This is a profile section AA. Looking at it across, and that's how the slab is performing. This is the critical area. We ran the number, deflection number 1, deflection number 2, deflection number 3. That's 0.5, 6, and 7. 5, 6, and 7. This area here, we found L over 14909, which is very small, and is a lot less than L over 360 of 1 inch over 30 feet. Then we ran deflection 2, which is points 4, 5, 4, 5, 6, and 7. We got L over 1642, and the deflection number 3 area was 3, 4, and 6. 3, 4, and 6. And basically this was L over 9, 5, 6, very small. We calculated tilt was 0.03%, which is less than 1% of tilt. So this thing passed section AA. We also plotted the deflection of the slab, section BB. And we ran these points here. Deflection 1, 2, and 3. 1 is L over 9, 43, which is a lot smaller than L over 360. Points 1, 2, and 3. 1, 2, and 3. Deflection 2, L over 1169. That's points 4, 5, and 6. Right here. And deflection 3 was L over 1321, which is a lot smaller than L over 36, points 4, 5, and 7. 4, 5, and 7. So all the deflections and tilts were less than the allowable. And this is the third section, CC, which we ran the same things. Deflection 1, 2, and 3, L over 961, L over 1553, L over 1237. The first one, deflection 1, was 0.4, 5, and 7. 4, 5, 7. This area here. Deflection number 2 was 3, 5, and 7. 3, 5, 7. Deflection there. Number 3 was 4, 5, and 6. 4, 5, and 6. So all of them passed. There was a tilt was 0.13%. And these are where all the actual deflections were a lot smaller than L over 360. So to summarize section AA, BB, CC, we measured these numbers of L over 1409, L over 943, L over 961, and all smaller than L over 360, so they passed. The tilt was 1% allowable. There were 0.03, 0.03, 0.3, they all passed. So from a deflection standpoint, this thing passes the FPA SC1-13 guidelines, which is similar to the Post-Tensioning Institute requirements for allowable deflections on the floor slabs. We try to check the compaction of the soils. We couldn't get good samples under the floor slabs. They were so hard, so they were very compacted. Now remember, the higher the compaction, the higher the swell. So the more the soil is compacted, the more swelling you're going to get in expansive soils. But in our opinion, the compaction on the soil floor slabs was good for settlement, but not for heave. No groundwater or perched water was observed during our excavations or test pits. We plotted the moisture versus depth at these locations. This is exterior boring B1, the red stuff. And we see the moisture was average in that location. This is the dry, this is the wet moisture, and here's the dry. The blue one is the dry you can get from TxDOT 124. TxDOT 124 procedure for PDR gives you the maximum dry moisture condition and wet conditions. In this case, was wet, average, dry moisture conditions at boring B1. Boring B2 from 0 to 5 feet, the moisture was average. Then it jumps to a dry. So what it's telling me is the top 5 feet of the soil in the exterior were wet. Below it was dry. Here again shows boring B3 exterior. It was average near the top 5 feet, then it jumps to about dry conditions below 5-7 foot. Boring B4, basically pretty wet, top 10 feet, then it moves to a dry condition. Boring B5 exterior, pretty wet, top 7 feet, then it moves to a dry condition. And again, this is the interior boring. You see the boring B6 interior moisture conditions was, this is wet, dry. The green is wet. It's kind of an average conditions, top 5 feet. Boring B7, average moisture conditions, top 7 feet, then jumps to dry conditions all the way to 10 feet. Boring B9 interior, it was kind of wet underneath the slab to depth of about 6 feet. Below that, it jumps to a dry condition. Boring 10, it was kind of average conditions, then becomes kind of wet, then it becomes dry. Below 7 feet becomes really dry. Boring B11, kind of a wet conditions all the way from 0 to about 5 feet. Liquidity index is another soil property that we measure. Liquidity index is the moisture content minus plastic limit over PI, plastic liquid limit minus PL. It kind of gives you how wet your soil is in terms of how far the natural moisture content has progressed between plastic limit and liquid limit. And Anything above 0 indicates the soils are kind of a wet. So if you plot the borings, the top 10 feet of it, liquidity index, you see they're mostly wet. These are exterior borings. For the interior borings, and we measured everything above 0, which means that average moisture conditions under the floor slab areas was wet too. So both interior and exterior, from a liquidity index, they were on the wet side in the top 5-10 feet. That means most of the heave has already occurred. Rainfall. The building was built in or about 1996. In 1996, we got a total of 36 inches of rain. Average rainfall we get in Houston is about 50 inches. In 95 was 50.2 inches. In 97, we got 71 inches of rain. What does that mean? When they built the building, the ground was kind of dry. Then it rained a lot, so it heaved. So what happens is you get edge lift at the edges when you build in a dry condition, and then you get a bunch of rain the next year. So it allows that edge heave, that basically the floor slab is kind of like a bowl deal. The edges, it starts heaving. GPR evaluation. The GPR data show, for example, this is a boring B11, and we found potential void conditions at depth of about 3 feet. Okay, here's another one, boring B9, near boring B9. The GPR showed a void area about 4 feet, and then high moisture area about 7 feet. The blue is all more high moisture, and this is the pink is kind of potential void. Again, here is near boring B8. These are potential void areas at about 4 feet. High moisture areas about 6-7 feet. That GPR shows. This is near boring B7. You can see the void here at 4 feet, and then high moisture area below about 5 feet or so. You see this big blue area, high moisture. And again, this is boring B6, high moisture area below about 2.5, 3 feet. Concrete floor slab strength and evaluation. We looked at that before. The spec called 4,000 PSI at 28 days. When we measured, most of our cores were more than 4,000 PSI. So the strength passed. No problem with the concrete strength. So why do we have all these problems? Well, generally, the problem with foundation problems like this are as a result of inadequate design, poor construction, poor quality materials, poor foundation maintenance. So in terms of design, there was a geotechnical report, which didn't have a copy of it, but basically they went out there, put the building in highly expansive soils on spread footings with a PVR of 1.9 inches on expansive soils. That's not a good design. God knows how many times I tell the structural engineers, don't put spread footings in expansive soils, and they still do it. And then the other thing is they suggested void boxes underneath the grade beams. When we went out there, did our test pits, we didn't find any voids. There may have been void boxes there, but there was no no voids underneath the floor slabs. That means the soil had already swelled into the voids. Construction. The exterior beams were at the grass lines. We like to have the exterior beams extend 6 inches above the grass lines. Materials. We tested soils underneath the floor slabs. All the fill materials, for the most part of it, they were fat clays. The select fill that's supposed to be underneath the floor slab should have a liquid limit less than 40, PI between 12 and 20. But most of the PIs that we got under the floor slabs were 40, 50, 30. So they put the wrong fill material underneath the floor slabs. Maintenance. Okay, we got bad drainage. We got negative drainage next to the foundations. That's bad. You don't want to have water going to your foundation. You want water away from the foundation. Plus that, we found trees next to the foundation system with root systems going underneath the foundation, going towards the foundation. University of Texas did some research. They said if you put a tree next to a building, as a distance of equal to the future height of the tree, D over H of 1, you can have differential movement of as much as 0.2 feet. That's 2.4 inches. So you can get edge settlement of 2.4 inches because of the presence of those trees. And we had a lot of trees next to the foundation. We had poor drainage, gutters next to the foundation. These are all maintenance issues. Bad planter areas. In summary, we feel like the stress occurred as a result of use of spread footings and expansive soils, which is a design defect, absence of void boxes, construction defect, placement of the building at the grass line, construction defect, poor quality fill with the high PI under the floor slabs, material defect, presence of the trees next to the building, maintenance defect, poor drainage, maintenance defect, depressions and holding water at the gutter areas, maintenance defect, repair. So what we try to do, come up with economical repair here. Technically, from a structural standpoint, the building hasn't really failed that bad. So we gave them 2 levels of repair techniques. One, that you don't have to spend very much money. One, you got to spend a little bit of money. Remember, we cannot go underpin this huge building, costs a lot of money, and this is a police station. You cannot disrupt the building operation. So what we recommended out there to go in there and take care of the landscaping, make sure you got good drainage away from the building, put some area drains around the building if you cannot get 5% drainage. Put in, and also we recommended putting some moisture barriers and root barriers. These function as a root barrier. When the roots hits it, it doesn't go underneath the grate beams and suck the moisture out. And also it will work as a moisture barrier. It keeps the moisture under the slab constant. If the moisture under the slab does not change, your building's not flapping. So as long as you keep this thing constant moisture, it doesn't flap. We recommend the moisture barrier of 5 foot deep. Positive drainage. We put either underground guttering system, or if you put splash boxes so that the water would drain away from the building. We don't want to have water drained right next to the foundation. We need to have a slope within 10 foot of the foundation. No ponding of the water should be allowed next to the foundation. Make sure you check the roof. Make sure the gutters can take the rain. We don't want to have the water splash over the roof into the planter areas. Replace the cracked bricks with new bricks. Fill the joints in the sidewalks around the slab so that the surface water does not have to get in there and cause a shrink swell of the soil. Okay, so you do that and you maintain it for a year to see if you're going to have movements. And of course, you run micro elevations every 3 months to see how much elevation difference you're going to have. If the movement stops, then you're done. If it doesn't, then we recommend that go to the next step, which you do all the level 1 repair techniques, which was drainage, moisture barriers. On top of that, go do chemical injection. You do chemical injections to a depth of 10 feet. You do the whole slab areas and 5 foot around the slab as sidewalks. You got to wait 72 hours and get soil samples to see if the chemical injection was affected by running swell tests. The maximum swell should not exceed 0.8%. Chemical injection, you chemically inject these chemicals that like sulfuric acid into the soil. And basically chemical injection pre-swell the swell sites, parking areas and pavements. These are the tanks that you mix the chemicals. And what it does is called cation exchange. These are clay platelets. They got negative charge. Water has got positive charge, so they want to absorb it. As they absorb, the clay expands. You get more water in the clay platelets, double layer. And so as if you reduce the water demand and reduce these negative charges, it doesn't swell as much. So it's called cation exchange, where it removes sodium, potassium, and put calcium in there in your soil. double layer. Depth of injection should be at least 10 foot in Houston area and in about 15 feet in Dallas, San Antonio, and Austin. This is Sienna Plantation. They don't chemical injection before they build the buildings, just kind of like before construction. You do chemical injection, these chemicals come out like that. This is an apartment complex doing chemical injection. This is the hole for the chemical injection. So for our building, we had to drill a hole out there in the floor slab areas at various locations. This is the hole right there. That's the key. It's not very big. You put the probe in there and chemically inject to a depth of 10 feet. After you finish, you grab the top of it, of course. But this is how you chemically, under pressure, you put the chemicals into the soil. You put them on like 2 foot spacing. And then you go do soil tests after that to see if the chemical injection reduced the swell. These are, again, the probes chemically injected, the floor slab areas. This is the areas that were chemically injected. Clean it up. You do interior and exterior injection. Questions? Any questions? Everybody was quiet, so I guess that was pretty self-explanatory. So I don't know what they're going to do with the building there. So hopefully they will maintain it and it will perform fine. We would be very interested to see what City of Sugar Land come up with in terms of performance. Any questions? Well, my name is David Eastwood. If you need to reach me, my email is de@geotecheng.com. And you can get a hold of me. I have an app in here for trying to do a poll. I don't know if it's coming up or not, but I'd like to see what you all think of the program. Let's see, it's not coming up. Yeah, please fill in the poll on this thing here. I don't know if you're getting it or not. Vicky, can you come here, please? Yeah, I got 3 questions here. Okay, thanks, David. Thanks, always do great. Any questions here? And the poll is not coming up.
Polls.
No response. Is anybody getting the polls?
It didn't pop up on my computer yet.
Great job. Thanks for the time and expertise. You're welcome.
Well, that's what it, like I said, I'm over there on my end trying to do it, but it ain't going to have either.
No poll here. I think there's a problem with this software Zoom that you cannot get polls anymore. Well, I appreciate you all's time here, and let's see, I got some questions, looks like it. No polls, no polls. Well, did y'all like it? If you like it, send me an email if you like it. And if you have any questions, shoot me an email later. I'll respond. And if you got any forensic projects, we surely like to take a look at it. And thank you very much for your time. You all have a great day. Bye-bye.